Okay, good afternoon for me. Good evening, afternoon, or morning for anyone else. I don't know when you'll be watching this, but this is Calculus 1's. This is Fall 2017 Exam 2. This is now my fourth exam too. I'm really starting to get a hang of all of this, relearning all this Calc 2 stuff, which is really just a ton of derivatives. So, yeah, they're not so bad derivatives at least at this point compared to like the future calculuses. It's just a lot of like product rule, quotient rule, chain rule. Those are pretty common practices that you'll see in a lot of these questions. So let's start with this first one. This is a pretty basic derivative question. It says, what is the slope of the tangent line, which is keyword for take the derivative. And then after you do that, plug in 4 for x. So let's do that, taking the derivative of this. Um, I think it would be really useful to, at the start, we can rewrite these square root of x's as x to the 1/2 power. And by doing that, it makes it clearer that we can just do the power rule, or the exponent rule, whatever you want to call it, where you just bring the power up front and then reduce it by 1. So let's go ahead and do that. This becomes 2x to the 1/2 minus 1/2 times x to the negative 1/2. 1 over x is just the same as like x to the negative 1, or more generally 1 over x to any power, let's say like a, that just equals x to the negative a power. So you just bring that exponent up and then make it negative. So that's how you can kind of take variables that have exponents and move it up to the top if they're the denominator. So now we're in this state and we can go ahead and do our derivative now. We can take the exponents and move them out front and get our answer. So 2x to the 1/2, this becomes 1/2 times 2, which is just 1, times x to the negative 1/2, because 1/2 minus 1 is negative 1/2, and then minus the next term. So we bring the negative 1/2 out front. Negative 1/2 times positive 1/2 equals 1/4, so minus 1/4. And then that gets changed because it's a negative here and then a negative here, so that's a positive. And then times x to the negative 3/2. So now we've taken the derivative now. We can before we go ahead and plug in 4 for the x's, we can revert these x to the negative 1/2 and this x to the negative 3/2. We can revert it back to how it was with like the square roots and the denominator and things like that, because that makes it clearer now how to actually interpret those as like square roots and stuff when we plug in 4. So we can do that. Next, the negative 1/2, we said before, that's the same as 1 over the square root of x, and then plus, okay, so 1/4, so this would be 1 over 4 times x to the negative 3/2, that's the same as x to the positive 3/2 in the denominator, and x to the negative 3/2 is the same as, I believe, the square root of x cubed. The 3 is there and the 2 is there, a square root. So that's where those come from, and now we can plug in 4, and then we'll get our answer. So all right, this becomes 1 over square root of 4 plus 1 over 4 times the square root of 4 cubed. 1 over the square root of 4 is 1/2 plus 1 over 4 times, okay, so 4 cubed is 64, and the square root of 64 is 8. So that's 4 times 8. This is 1/2 plus 1 over 32. Now to get these in, common denominators, let's see, this can become 8, no, not 8 over 32, 16 over 32. That's the same as a half. And we have the same denominators now, so this is now 17 over 32. So that's how you get the answer of D. Um, just to recap, pretty standard derivative question. When you see slope of the tangent line, you definitely want to be doing a derivative at some point in your answer. And as far as the derivative went, just remembering that square roots are the same as raising something to the 1/2 power, and that anything in the bottom you can just put it on the top to make it easier by just adding a negative sign to it. and then lots of power rule and just the exponent rule where you take it out front, and that was really all there was to it. All right, number two. All right, just a standard derivative problem. Take the derivative of the function and then plug in 1 for x after you do the derivative. So, okay, first thing we should do to do this derivative, we have a quotient, we have a fraction, so we should do the quotient rule when doing this. So, quotient rule is when you have an a and a b, a numerator and a denominator, and you take the derivative, that's the same as a prime b minus a b prime all over b squared. So we can use that template and then fit it to our actual problem. So let's do that. So a prime, this is the derivative of x squared plus 1. So that's the same as 2x. And then times b all by itself, this is x cubed plus 1 squared. And then minus a all by itself unchanged, x squared plus 1 times the derivative of b. So now we have some sort of like nested thing. So taking the derivative of b, well, we're gonna have to do the chain rule because we're gonna put the 2 out front and then multiply it by the derivative of the inside. So we do that, we get 2 times the inside unchanged, x cubed plus 1, and then times the derivative of the inside. Derivative of x cubed plus 1 is just 3x. And then this is all divided by the bottom squared, which is x cubed plus 1 to the fourth. So now we have our derivative. I would not recommend simplifying this. I never really recommend doing that after you do your derivative. It's just unnecessary work, and you'll have a higher likelihood of messing something up and getting a wrong answer. So I'm not going to simplify this at all. I'm just going to immediately plug in 1 for x and then see what we get by simplifying after. So let's do that. So this is 2 times 1 is just 2. 1 plus 1 is 2, and then squared, minus 1 plus 1, which is 2, times 1 plus 1, which is 2, times 3. Lots of 2's. That's pretty cool. And then this is going to be 1 plus 1, which is 2 to the fourth. So simplifying further, we get 2 times 2 times 2, which is 8, minus 2 times 2 times 2, which is 8, times 3, which is 24, all over 2 to the fourth, which is 2, 4, 8, 16. And then this becomes negative 16 over 16, which equals negative 1. So yeah, recap, just quotient rule, exponent rule, chain rule, and then what I never like doing is simplifying after you get that first derivative. Just instantly plug in the value it gives you, which is 1 in this case, and then you'll probably mess up less when you do that. Sorry, skipped over my words. All right, number 3. This is gonna be a quick one. It's just one of those like knowledge nuggets that they sometimes throw at you, like, hey, do you know this one specific thing about this one specific other thing that we know? So it's just 3 prompts asking us about the inverse trig function of the trig function of 2 pi over 3, and it's asking us for these 3, sine, cos, and tan, if the result is the same thing as what we put in, 2 pi over 3. So so to solve this problem really quickly, you just remember that the range of the 3 main inverse trig functions, sine, cos, and tan, are as follows. So for inverse sine, it goes from negative pi over 2, negative pi over 2 to pi over 2. So if we have our unit circle, it goes from negative pi over 2 to pi over 2 up there with the 0 right here. So pi over 2, negative pi over 2, pi. So sine is right here. This is the range of inverse sine. And since 2 pi over 3 is outside of that range, it means that when we do this whole thing, we plug in, we do a sine and then we do an inverse sine, it will not be the same like the answer that it gives here. It won't be 2 pi over 3. It will be instead, it looks like sine is like up and down. So if you do 2 pi over 3, which is like about right there, it will actually return pi over 3 instead. So that's what happens there if we do 2 pi over 3, so we know that 1 is false. Now what about 2 for cosine? So cosine is from 0 to pi. So it is this arc right here. And hey, 2 pi over 3, which was right there, uh, 2 pi over 3, that is within that arc, which means that if we plug in 2 pi over 3 into cosine and then do the inverse cosine, we will get back 2 pi over 3 instead of a different angle. And just to prove it to you, this line right there, that represents 2 pi over 3. So it will return, the cosine, it will return negative a half. And then what inverse cosine does is it puts it back out here and then measures this arc here, which is 2 pi over 3. So get the same angle when we do cosine and then inverse cosine. So that one is true. Now what about 3? Well, actually, we can already figure out that C or B is our right answer. But let's work through 3, the tangent first before we move on. Tangents range, inverse tangents range, is the same as sine, inverse sine. So it's pi over 2 to negative pi over 2 to positive pi over 2. So again, it's this arc here. 2 pi over 3 is not within that arc, so when you do the inverse tangent of the tangent of 2 pi over 3, you will get something other than 2 pi over 3. In this case, I think you'll just get pi over 3 again, which is right there. So we know that one is false. We know that B, 2 only is true. So yeah, again, that was just like a thing you gotta know, like a not really any calculation in this one, just something that it tested you on, like a little tidbit about your trig functions, your inverse trig functions more specifically. So I guess just this is not the only. This is a pretty kind of common-ish problem, inverse trig functions. So I guess it would be pretty good to know those. All right, number 4, evaluate this limit. So I'm going to do it probably in a different way that it wants you to do it. My weakness is that I have no earthly idea what to do with trig functions that aren't sine, cos, and tan ever. I have no idea what to do with them. Derivatives, integrals, whatever. So I'm going to turn these two trig functions into like, in terms of sine and cos. That would make it easier for me to deal with, so that's how I'm going to do it. First, we can turn this cosecant into 1 over sine. So this is 1 over sine of 3x. And then times 1 over cotangent is just the same as tangent, which is the same as sine of 9x over cosine of 9x. So now we're in this state. We're still taking the limit of all of this. I think our best next step is to remember that the limit of a product of two things is the same as the limit of one thing times the limit of the other thing. So we can do that, but before we actually do that, I'm going to rewrite this as limit of sine of 9x over the sine of 3x times cosine, or 1 over the cosine of 9x. I'm going to write it like that so then when we do this limit trick where it's limit of one times the limit of the other, this is a lot easier to take the limit of, and so is this, compared to the original two terms that we had. This and this. These two are not very fun to take limits of. I already tried that. So we'll do the thing I said where it's the limit of sine of 9x over the sine of 3x times the limit of 1 over cosine of 9x. So now we're here. Take the limits of each of them separately. So let's start with the left one here. We can realize that if we plug in, the value that x is approaching, which is 0, we get sine of 0 over the sine of 0. And that's just 0 over 0 in indeterminate form. So we can just do L'Hopital's rule for this part. So if we make two columns, one for limit of sine of 9x over limit of sine of 3x, we can do L'Hopital's rule and take the derivative of the top and the bottom. So derivative of sine of 9x is cosine, cosine of 9x, and then we have to do chain rule, multiply by the derivative of the inside. So derivative of 9x is just 9 all over. This will also be cosine of 3x times 3. So still doing the limit of all that. Um, Now if we just plug in 0, the value that x is approaching, we'll get 9 times cosine of 0, and cosine of 0 is just 1. So this is just 9 over 3, limit of, well, actually no more limits anymore. It's just 9/3, which is just 1/3. So this is now just 1/3. No, not 1/3, just 3. I don't know what the heck I'm doing. So 3 times, and then the limit of 1 over cosine of 9x. And again, that we just have a state where we can plug in 0 in for the cosine. So 1 over the cosine of 0 is just 1 over 1, aka 1. So it's just 3 times 1, which is 3. So that's how I would do the limit for this problem, just breaking up these weird trig functions into terms of sine and cosine. That makes it easier for me to deal with them. And then also this limit check that I didn't even know existed until I did this problem, where limit of a times b is the same as the limit of a times the limit of b. Same thing goes for quotients, like limit of a over b equals the limit of a over the limit of b. That's actually pretty useful. That I didn't even know was a thing until this question. So those two things, I think, make limit problems a lot easier. Okay, number 5. We have f of x, and that's actually all that. And we need to find f double prime of 0. So essentially, do two derivatives on f of x and then plug in 0. So first derivative, taking the first derivative of e to the 2x times cosine of 3x, looks like we'll do product rule here, which again, if we have a times b, taking the derivative gives us a prime b plus ab prime. So we can use that template, plug things in. A prime, the derivative of e to the 2x is 2e to the 2x times just cosine of 3x. Plus just e to the 2x times the derivative of b, so derivative of cosine of 3x. So this is negative sine of 3x and then times the derivative of the inside, which is just 3. So I'm going to write this as 3 sine 3x, negative 3 sine 3x. Okay, so we have our first derivative now. Normally, I say and I recommend never simplify your derivatives because that'll just introduce a lot more work that you'll have to do, and there's a lot more like potential errors that you can make. But since we need to do another derivative on top of this, we probably should simplify this because taking derivatives of not simplified things gets really messy. Like we could take the derivative of this, do a product rule here and then a product rule there, and then a lot of other things. We can simplify this a little bit and minimize the amount of work that we have to do for our second derivative. Once we get the second derivative, we won't do any more simplifying after that since we just need to plug in a value. But for now, let's simplify this. So looks like there's an e to the 2x on both sides. There's a term there in both terms. So we can take that out. This is now e to the 2x of, let's see, it'd be 2 cosine of 3x minus 3 sine 3x. I think that's how that works. And now we only have to do one product rule. We only have two things multiplied together instead of like 2 plus 2. So we can do our second derivative now. So again, a prime b plus ab prime. A prime e to the 2x, that's just, we already did that. That's 2e to the 2x times just the b unchanged, 2 cosine of 3x minus 3 sine of 2x, or 3x. And then plus a unchanged, e to the 2x times the derivative of the second, this. So let's see, derivative of 2 cosine 3x is negative 2 sine 3x times the derivative of the inside, which is 3, which makes that a 6, and then minus, okay, so 3, that's pretty janky there. Let me rewrite that. Derivative of 3 sine 3x is 3 cosine 3x times 3, so minus 9 cosine 3x. So, all right, so now we're here. Now that we're in a part where our next step is to just plug in 0 for x, let's not do any more simplifying. Let's not do any additional work. Let's just plug in 0. So plugging in 0 for x, this becomes 2e to the 0. E to 0 is just 1, so this is just 2 times, okay, 2 cosine 3x. Cosine of 0 is just 1, so this is just 2 minus 3 sine 3x. So this is 3 sine of 0. Sine of 0 is 0, so this is minus 0. You can really just forget about that, or maybe not erase it so people can see what I'm doing if they just skip to the end. And then plus e to the 2x. We kind of already did that. E to the 0 is just 1. And then 6 sine of 0. We already said sine of 0 is just 0, so this is 0 minus, excuse me, sorry, and then minus 9 of cosine of 0. Cosine of 0 again is just 1, so this is minus 9. So this is 2 times 2, which is 4, plus negative 9. So 4 minus 9, which is negative 5. There we go. Okay, so this is just a lot of product rule and a double derivative, which is just 2 derivatives. Again, when you do double derivatives, I always say don't simplify any derivatives that you do, but when you're doing double derivatives, it's helpful when your second derivative is simplified, or rather your first derivative is simplified, so then when you do the second derivative, it's a lot easier. So that's what we did in our, basically our second step. So in some cases you can simplify your derivatives, but in most cases just leave it as is. Okay, number 6, derivative problem. So we're given that, take the derivative. Don't even have to plug in any values afterwards. So to start with this derivative, I think it becomes clearer what we should do at the start if we rewrite this as x plus x to the 1/2 all to the 1/2. Because then it becomes clear we can do the exponent rule where we like take it out front and then chain rule multiplied by the derivative of the inside. And yeah, that's what we do. So all right, so chain rule now. So we multiply this by 1/2 times x plus x to the 1/2 raised to the 1/2 minus 1 is to the negative 1/2, and then times the derivative of the inside. So this is now derivative of x is 1, derivative of x to the 1/2 is 1/2 x to the negative 1/2. All right, so that's our derivative. We just, compile it now into a more legible form that it wants to see. So we can do that. We can substitute all of these 1/2 powers back into, square root symbols. So this becomes 1/2 times, whoa, actually before we do that, all of this is raised to the negative 1/2, which is the same as 1 over the square root of the inside. So this is now 1 over 2. So we got the 1/2 accounted for. Now it's the square root of the inside. So it's x plus the square root of x. So that's the left part now. And the right part is 1 plus, let's see, 1/2 times the square root of x, or on the bottom. So this is 1 over 2 square root x. All right, so we're almost done here. We just need to put these two terms together. I think before we do that, we could rewrite this into a better form without like a big fraction in it, because if we just chuck all of this, up in the numerator, I don't think that's technically fully simplified because we have like a fraction in the numerator and none of these have that. It's all just one fraction with no embedded fractions basically. So we can do a little better. Uh, we can combine this 1 and this fraction into one fraction by turning the 1 into, let's see, 2 root x over 2 root x. So then we have common denominators. And then that becomes 2 root x plus 1 all over 2 root x. And then when we go ahead and multiply it by the fraction we originally had, we get, let's see, 2 root x plus 1 times 4 root x times root x plus root x. Jesus, a lot of root x's. Um, and is that our final form? Yes, it is. It's that one down there. Um, yeah, so just rewriting square roots as powers of a half makes it clearer for me at least that you need to do the exponent rule. Um, and then what else in this problem? Just chain rule. Um, knowing when to rewrite things and simplify things so that when you simplify even more, it's fully simplified. That was a weird sense, but I think you get what I meant. Just knowing how to properly simplify things and crunch them down into the most simplified form. All right, question 7. If we have this equation here, what is y prime? Okay. All right, this is a classic implicit differentiation problem. So we're asked to find y prime, and you think, okay, first thing we should probably do is get this equation into a form where it's y equals, where you have y on one side, and then x terms on the right, and then take the derivative. That that is terribly complicated because we have this x squared y and this y cubed and then this y. That would be hellish to try to get all the y's on one side. So instead, what we can do is just do implicit differentiation, where you take the derivative of each term, like separately kind of, and then for every term that you take the derivative of a y, you multiply that term by dy over dx. That sounds a little weird and complicated, but I'll just show you what it means in practice. It's not that bad. So taking the derivative of all this, derivative of x squared y, okay, that's a product rule. So this is now derivative of x squared, that's 2x. Now we didn't take the derivative of a y, so we don't multiply it by anything, and then times y plus x squared times derivative of y. So derivative of y is just 1, and then we multiply it by dy over dx because we just took the derivative of y. So this is now 1 times dy over dx, or just dy over dx. So then plus the derivative of y cubed, this is 3y squared, times dy over dx because we just took the derivative of a y, equals derivative of x, which is 1, minus the derivative of y, which is 1 times dy over dx. All right, so now we have our derivative, and at this point we just solve for dy over dx as if it was just like a variable. And then once we do that, whatever's remaining, on the right side or the left side or however you want to do it, will be our answer here. So to solve for dy over dx, it's just like any algebra problem. You just get all of its terms on one side. So we have these terms to worry about. We can get them on one side. So this is x squared dy over dx plus 3y squared dy over dx. And then it would be plus dy over dx. We add dy over dx on both sides. And then that equals, let's see, we have this 1 still here, and then we subtract 2xy from both sides, so minus 2xy. So now we're here. We can take a dy over dx out of both sides, or not out of both sides, just the left side. Dy over dx times, let's see, x squared plus 3y squared, excuse me, plus 1 equals 1 minus 2xy, and then divide both sides by x squared plus 3y squared plus 1. So dy over dx equals 1 minus 2xy over x squared plus 3y squared plus 1. Is that an answer? Yes, it is. A. So yeah, implicit differentiation. This is a pretty good like default template problem to teach and learn implicit differentiation when you're actually doing it. It's just a bunch of things you already are learning in calculus, like the product rule and the quotient rule and the chain rule, things like that. So implicit differentiation problems are good, uh, like if you only study, if there's only one topic you could study in these exam 2 exams, implicit differentiation would be pretty good because it covers a lot of other things in calculus. All right, question 8. This is one of those questions where you're given a couple of like ambiguous functions. So we have this g of x, which is defined by this like combination of f of x's, and we don't actually know what f of x is. We're just given a couple key values for it, and then we're asked to find g's derivative and then plug in 1 for x. So take the derivative of this and then plug in 1. So let's do that. Take the derivative. Derivative of this term looks like we have an exponent, so we do the exponent rule where we take it out front. So that's 2 times f of x, and then 2 minus 1 is just exponent of 1. That doesn't do anything. And then we also have to do chain rule. So we take the we multiply that by the derivative of the inside f of x. So we just do times f prime of x. Okay, so that's the derivative of the first term. Second term, f of x squared. Okay, another chain rule, I think. So we take the derivative of the outside, which is just f of x, so f prime of x squared, and then multiply by the derivative of the inside, x squared. So that's just 2x. So now we have our derivative, and we just plug in 1 for x into all of this, and then we simplify. So this becomes 2 times f of 1, which is 2, times f prime of 1, which is 3, minus f prime of 1, 1 squared is just 1. F prime of 1 is, again, 3, times 2 times x, which is just 1. So now we're here. 2 times 2 is 4, 4 times 3 is 12, minus 3 times 2 is 6, 6 times 1 is 6, and we get 6. So that wasn't too bad. Actually, these problems are, to me, they're like the break of the exams. They're not really, they don't have a whole lot of calculation. It's just remembering that, even if you're not given, even if you don't have every function defined, sometimes you don't even need it. They'll just give you the values that you will actually need. And so if you like hop into the problem immediately and think, oh no, where's f of x? How would I do this? They've got you covered. So yeah, just basic derivative rules and remembering all that. All right, question 9. This is one of those like particle moving questions. Get out of here. Get that little bar out of the way. Is it gonna disappear? There we go. Anyways, okay, this is a particle question where particle is like moving by a specific like position function, or like you throw a ball up in the air or whatever. So it's one of those. A particle is moving on a straight line, so its displacement from the origin, aka its position. Displacement and position are like kind of the same thing. I know if you've taken physics, you might be screaming at me that they're different, but in this context, it's kind of the same. And it makes it clearer that we're talking about this, which is the position function, s of t. So its position from the origin is given by the position function, during which of the following time intervals is the particle speeding up. Okay, so these time intervals here. What it basically means is like, let's say A is like the correct answer. So what we'd say is that the particle is speeding up whenever it's like after 2 seconds. So from 2 seconds to infinity, the particle is speeding up. If it was like E, then we'd say the particle is speeding up between 0 seconds after takeoff and 2 seconds after takeoff. Anytime after 2 seconds, it's either slowing down or has a constant velocity. It has no acceleration, basically. So how do we do this? Well, I just said acceleration, and you might be able to infer that by the word speeding up there. Think about like when you're in your car. When you speed up in your car, you're holding down the accelerator. You're accelerating. So we should be thinking about the acceleration function. And how do we get the acceleration function? Well, acceleration is the derivative of velocity, and velocity is just the derivative of position. So basically, if we just take the second derivative, or two derivatives right in a row on the position function, we'll get the acceleration function. And that'll make it a lot easier. Actually, it might be the only way to figure out these time intervals. So let's go ahead and do two derivatives. So v of t, actually, let's put it up here. V of t equals the derivative of s of t, which equals 3t squared minus 6, nope, minus 12t plus 12. You can forget the 8 because that's a constant, and the derivative of a constant is just plus 0. So just ignore it. And then the acceleration is equal to derivative of velocity, which is equal to 6t minus 12. Same situation here. We can just forget the plus 12 because it's a constant. So now we're here. We have our acceleration function. Now, how do we figure out uh, which, x values basically are going to make this particle speed up by using the acceleration function? Well, what we can do is we can set this equal to 0. So 0 equals 6t minus 12, and then solve it. So let's do that real quick. That's equal to 0 equals, divide everything by 6. That's t minus 2. So we know that t equals 2. So what this t equals 2 means is if we draw like a number line like this, and we put 2 right in the middle, it means that this is like a divisor where everything on one side is going to be speeding up and everything on the other side is going to be slowing down. So now we're in this position, and what we can do to find which side is speeding up and which side is slowing down is just by taking two random points from each side and seeing if they're positive or negative. And to be clear, we plug them into our acceleration function here. So any 2 points will work on either side. We can just do the closest like whole numbers like 1 and 3. It's usually easiest. So we can do that. Acceleration at 1 is equal to 6 times 1 minus 12. That's equal to negative 6. So that's negative. So we know that our drawing our diagram, anything, on the left, basically anything containing this 1, it must be negative, aka it's slowing down. And then when we think about t equals 3 right here, this is now a of 3 equals 6 times 3 minus 12 equals positive 6. Okay, so then the right side, anything after 2 seconds is speeding up. So how do we take this? So this is what we're looking for, by the way. What time interval is speeding up? It looks like it's any time from 2 seconds after takeoff to looks like infinity. So we can say that is A. That's exactly what we're looking for, from 2 seconds after takeoff to infinity, forever after 2 seconds. So that was a bit of a long one. Looks like it was two derivatives to find the acceleration function, to find when it's speeding up. That's a good thing you can look out for, is language like that, like speeding up, or um, I guess maybe if they're looking for velocity instead of acceleration, they would just be looking for um, moving to the right or something. And then yeah, just some derivatives, and then the basic like exponent rule, and then oh yeah, we had the diagram down here, the number line where we figured out which side is slowing down, which side's speeding up, plugging numbers into the old functions, and yeah, this was just a memorizing the process question, I guess, where like the individual steps weren't too bad. It was just derivatives and stuff, but knowing how to do the whole thing, that's, I guess, where the challenge is. So maybe this topic here, I don't know what topic I'm going to call it, but like you just sort by topic at the top and then do more of these. That'd be really effective. Okay, question 10, one of these rate problems. So if the half-life of a radioactive substance is 7 days, how long does it take for that substance to lose 2/3 of its original amount? So let's remember that what that formula was again. It's the final A of t equals the initial A of 0 times, usually it's E in the base here if you're doing like compounded interest money stuff. But in this case, we're doing half-lives, so this needs to be 1/2. raised to the power of n. Sometimes there's like r's and t's. I'm going to make it a little simpler here and just do n. And this n will represent the number of, how would it be? It's the number of half-lives that elapse over a given period. So basically, we're going to solve for n, and then that'll tell us the number of half-lives that elapse in our given amount that we're trying to find. So when we solve for n, we just multiply it by the half-life length, which is 7, and then that'll give us how long it takes for it to lose 2/3 of its stuff. So hopefully you got that. Let's solve for n now. We'll see that the initial is just actually the final is actually just the initial times a third. So 1/3 a equals a times half to the power of n. So we can get rid of these a's now. So it's now just a third equals a half to the power of n. And we'd want to solve for n, so we'd probably just do the ln of both sides. Before we do that though, let's realize that so taking logs of fractions gets kind of messy sometimes, and you'll see that none of these ln's in the answers here, none of those have any fractions. It's ln's of actual whole numbers. So let's rewrite this as a third equals 1 over 2n, and then we can flip all of the fractions, so this becomes 3 equals 2n. That is a lot cleaner. So now when we take the ln of both sides, this is ln of 3 equals ln of 2 to the power of n. This is n times ln 2, ln 3, so n equals ln 3 over ln 2. That is a lot simpler than I think it would be ln of 1/3 over ln of a half, I believe. So that looks cleaner, and it's aligning a lot better with what these are looking like. There's a lot of ln3s and ln2s in here, right? Like ln2, ln3. So we know we're kind of on the right track. So now that we have our ln, remember that represents the number of half-lives that are the number of half-lives that elapse over the given period. So when we multiply by the given period, we'll get no, if we multiply by the length that it gives us, which is 7 days, we'll get our desired how long it takes for it to lose a third of its stuff. So we do this and we multiply it by here is 7, so this is just 7 times ln 3 over ln 2, and that's b. So, God, I do not really like these problems because it doesn't really it's just a formula that you plug numbers into, and that's not a whole lot of fun, just remembering stuff. And B, it's not very intuitive to me. It's hard to stay down to earth with these problems. Like, it's hard to realize you're doing the right thing. You kind of just take shots in the dark and do a bunch of weird, simplifying tricks to get the right answer eventually. So it's not very easy to intuit, and that's why I don't really like it. But that's how I would do this problem. I had to look it up on Google how to do it because I didn't even remember how to start it when I reached this problem. So yeah, so the original equation, which was a of t equals a of 0 times, usually it's e, I'm just going to rewrite e here to n. Sometimes n will be rewritten as r times t, I think. R times t. So yeah, so the principal times e to the rt, p-e-r-t, pert, that's what I use sometimes. So the original formula, knowing which each of these variables equals, or means, that'll maybe, hopefully, get you on the right track to the end of the problem. All right, question 11, we're almost there. If f of x equals, okay, derivative problem. So f of x equals this, x to the ln x, find f prime of e. So I'm immediately scared of this problem because it's so short. It's literally 1, 2, 3, 4, 5 words. Problems that are only 5 words, they're the most complicated of them all. So I'm hoping this won't be too bad. So taking the derivative, I don't think we would want to use implicit differentiation for this because there's no y, and also we're only given an x value. Usually for implicit differentiation, you're given an x and a y value. but that I don't think that's going to work here. So we can just do a raw derivative and tackle this. So um, first thing I do is something pretty, I don't really use this often. It's called it's like a different kind of exponent rule, different kind of power rule where, so usually you're asked to do the power rule of like x to the 2 or x to the 20, but sometimes if you have x to the power of something else that has an x in it, like ln x, you do something a little different. So I'm going to generalize this. If you have a to the power of b, that equals, you just rewrite a to the power of b times the derivative of a big thing, which is the ln of a times b. So you do a to the power of b times ln of a times b, and then the derivative of ln of a times b. So when we follow that, that will end up equaling, so f prime of x, that equals, let's see, a to the power of b, which is just the original, x to the ln x, times uh, the derivative of ln x times the top, which is also ln x. Okay, we have two ln x's here. So now we can, let's probably combine those. Ln x times ln x times ln squared x and prime. So that equals x ln x times, let's see, the derivative of ln squared x. This is power rule to start. So x times 2 to the ln of x, and then that's 2 minus 1 is 1, so it's ln to the power of 1, which is nothing. We have to chain rule this too, so we multiply by the derivative of the inside. Derivative of ln x, you should remember that that is equal to 1 over x. That is I highly recommend you remember that the derivative of ln x is 1 over x. And the opposite, so the integral of 1 over x is equal to ln of x. So probably won't do integrals for a little bit, but that's good to keep in mind. So we're here now. So I actually think we can just plug in e at this point, and we can get our answer. So okay, so this is now e to the ln of e times 2 times ln of e, which is 1, times 1 over e. So we're here now. This is, let's see, e to the ln of e. ln of e is just 1, so this is just e times 2 times 1 over e. These two e's cancel out, and we're left with 2, c. So yeah, this is just a generalized power rule problem. Remembering what this obscure equation is. I don't even remember learning that in Calc 1, but I think that's what you're supposed to do here, where a to the power of b is equal to a to the power of b times the derivative of ln of a times b. That's kind of weird, but I guess that's how you do it. Just remembering that and then simplifying, that's how you do this problem. All right, question 12. This problem sucks because it's literally just, well, it's short because it's literally just asking you to regurgitate this one little piece of information that I don't even know. It's so weird because it's this sine h thing, which I have no idea means at all. It's something to do with like hyperbolas or whatever. So I have absolutely no clue. I've taken 3 calculuses and linear algebra. I have no idea what it means. So solving for x, this is you could probably guess we just take the inverse sine of both sides. So because inverse sine h of sine h of something just equals the original something. So this just means x equals inverse sine h of, let's see, 1. Like that. So all it's asking you is to remember what inverse sine h means, which is so weird. I don't know why they're asking you about this. Inverse sine h of any value, let's not say x, let's say like a, that just equals the ln of a plus the square root of 1 plus a squared. Why would you ever need to know that? I have not seen this come up at all yet. It's so weird. So when you plug in 1 for a, you get x equals ln of 1 plus the square root of 1 plus 1 squared. That equals, let's see, ln of 1 plus I wrote that weird. 1 plus the square root of 2. That is exactly our answer B. Um, why the hell is it asking about the inverse sine h function? No idea, but it is. It's the first time it's asking about this. I doubt it'll appear in any of your exams, but that's how you do this by just remembering that inverse sine h just equals that big function. So it's whatever. They usually like to put their weirdest questions at the end, at question 11 or 12. But anyways, that was this whole exam. I did this over 2 days, over like an entire week. So I kind of figured it was on like the first half, because I was doing stuff. So let's see, derivative, probably a lot of derivatives. Okay. Oh yeah, this like trig function thing. That's useful to know. Evaluate a limit. Let's see, that's important. Two derivatives, the second derivative. Another derivative. Uh, oh, that one fun like plugging in values question. I liked that one. Particle moving, that which is also just derivatives. Half-life question, I don't like those. Derivative and again this stupid question. So, uh, yeah, you've probably felt by now that a calculus has lots of derivatives in it. So for these exam twos, it's really nice to lock down those basic derivative properties like uh, there's the power rule, which is everywhere, and then there's also the quotient and a product rule. And then there's also, let's see, there's trig, like when you take the derivatives of trig functions, derivative of sine is cosine, derivative of cosine is negative sine, things like that. Um, just a billion derivatives on these exam twos and three and the final. So yeah, get good with your derivatives, guys.